us start with the theory of probability. So the very first question that comes to our mind is, what is the need to study probability at first place? Before even studying probability, we should ask, why are we studying this particular topic? So we are studying probability because in real life, whatever is happening, there is a certain chance of that event to occur. That means based on the previous events or the past events, we can describe the probability. For example, suppose a normal human being who does not know mathematics or statistics would say there would not be any rain today based upon the weather conditions. If there is a bright sunny day, so he would conclude by looking at that sun present in the sky, the person would say there won't be any rain today. But if there are some clouds which are present in the atmosphere, so the person would conclude that, or he will comment that there will be rain today. So this is what a person without mathematical knowledge would say based upon the observations that there is a cloudy sky or there is a clear sky. Whereas a mathematician or a person knowing statistics, the person would say that, okay, based upon the weather conditions, they would conclude that the probability of rain is 0, or they would say the probability of rain is 1 today. So that means they are saying this on the basis of their observation also, but they are now saying that the chances of happening of rain is 0 in this first case and that of 1 in the second case. So so that is the need for studying probability, because it tells you the uncertain events that you cannot directly say. Suppose there is a sun outside and there are some clouds, so what would you conclude from that? Would it rain or would it not rain? So that is unlikely event. That means there is a quite amount of uncertainty which is involved in that particular event. So we say between 0 and 1 there is a chance of occurrence of event. So what numerical quantity can we assign to that uncertainty? That is what the theory of probability will tell you. So having known this need, so let us now discuss what is probability. So it describes the happening of an event with that event is uncertain based upon the past experiences. So this is probability. So it basically measures uncertainty, and whenever its value is equal to 1, we are sure that that particular event will occur. For example, in these particular days, we will say there will be online classes due to COVID. So this is certain, the classes will held, and the probability of occurrence of class is equal to 1. But in certain situations, we say that there is the probability of happening of an event is equal to 0. So that means we say this event will not occur at all. So this is an impossible event. So for example, you could say that the chances of students to visit university during this COVID era that are 0, because it is the government order that you cannot come to university because of these COVID crisis. Okay. And suppose we have uncertainty and we cannot say it is surely equal to 1. We are not certain that it will happen, and we are also not sure that it won't happen. So what would be there? It would be in between 0 and 1. So in that case, we are unlikely, we are not sure, and we are unsure, and there is a huge amount of uncertainty that is present there. So for example, a question, when the era of COVID will end. So this is the question which nobody could answer certainly, that okay, will it end today or not. So there is a quite huge amount of uncertainty that is involved in this probability. So before defining the formal definition for probability, let us understand few of the terms. So the first term that I have listed over here is random experiment. So what is random experiment? So here we have two terms. One is this random, another one is this experiment. So what is experiment? Experiment is something that you perform under identical conditions. That means it should not be like you are performing the experiment today and you are performing the same experiment after 6 months at some other place having different environmental conditions. So obviously the results would be different, but if the experiment that is performed under identical conditions, then also the results could be different. So random experiment means every time the result of an experiment is random and you are not certain, we are not certain what could be the result. What could be the result of the particular experiment? So that is random experiment. So next, what are outcomes? Outcomes are the results that you obtain, results obtained when a random experiment is performed. Now suppose I give you a task, okay, go and you have this coin with you, okay, 50, say 5 rupees coin. This is a 5 rupee coin. So I give you an experiment that you go and toss this coin, say 1000 times. So it will be a huge experiment. So you will repeatedly do this experiment, and whatever is the result, in this coin there are two faces, one is head, another is tail. So in each of the experiment, either you would have head or you would have tail. So that means two possibilities are there in one trial. And how many such trials are you performing? You are performing 1000 trials. So every time you are tossing this 5 rupee coin, so that means each time you are having two results, next time also you would have two results, next time also you are having two results. How many times? You are doing this for 1000 times. So that means the total outcomes or the results for this experiment would either be head or tail. How many times? 2 to the power 1000 times. So these are the outcomes that you would obtain when you perform this kind of experiment. So next we have another term which is the events or trial. So event, if in the case of this head or tail experiment, what is event? Whenever you perform this experiment of tossing a coin, what is the event? Event is something that you will get. So event here in the case of tossing a coin is either a head or a tail. So these are the only two possibilities that you could obtain. So that is an event. For example, suppose we have some seeds with us. We have some seeds with us. So now one could go and sow some seeds. This is some farm and a person is sowing some kind of seeds over here. So now out of these 10 seeds, okay, suppose we have 10 seeds. Now what would be the outcome? So here the random experiment would be sowing seeds. So random experiment here is sowing seeds.
Excuse me, ma'am.
Yes.
Ma'am, your screen is just stuck into a page of probability of the first one only.
Okay, let me check. You are given this random experiment that you go and sow 10 seeds into the field. So this is the given field and you wanted to...
Ma'am, the screen is stuck.
So next we have exhaustive cases. What do you mean by exhaustive cases? That means the total number of cases that you could have. So all the possible outcomes, all the possible outcomes that you can have out of a given experiment. Suppose in this case you roll a die. You have a die with you and you roll it. So after rolling that particular die, so either you would have 1 or you would have 2 or you would have 3 or you would have 4 or 5 or 6. So either of these 6 numbers would come up on the top of that die. So the total events here or the total results here, they are 6 in number, and this is known as the exhaustive cases. Exhaustive cases means the total number of outcomes. So this is exhaustive cases. Next is the favorable cases. Now out of these total cases, the total cases, we are interested in certain particular cases. So depending upon our interest, the events become favorable cases. For example, now you are going to that particular field where you have sown your 10 seeds. So now in order for these seeds, now one person wants, okay, how many seeds will germinate. So that is the interest of one particular person who wanted to see what is the quality of the seeds. So that becomes the favorable event. So favorable event in this case would be the number of seeds which will germinate. And another person who wants to look at again for the quality, but he will now see how many seeds are there which will not germinate. So in his case, he is interested to see those seeds which are not creating plants. So the favorable cases would be the number of seeds which are not germinating. So it depends upon the interest of different people. Next is the mutually exclusive events. What are mutually exclusive events? They are events which are independent of each other, or we are saying whose occurrence is independent of others. That means, suppose we have some event A and we have some event B. Now we say the probability, there is nothing common between A and B. So we say the intersection of A event and B event is phi. Phi is the empty set. So that means they do not have anything in common. For example, when you toss a coin, so the outcomes of this experiment, they are either you would obtain head or you will obtain tail. So in this particular case, if you obtain head, that has nothing to do with tail, and if you obtain tail, that has nothing to do with head. So these two events are mutually exclusive. Why? Because their intersection is equal to phi. Whenever you would have head, tail would not come up, and whenever you have tail, head would not come up. So they are mutually exclusive events. And suppose this is the total sample space you have, or the what do you mean by sample space? Sample space is something where you list all the possible outcomes. So this is some set where you list all the possible outcomes of the given random experiment. So now suppose this is some sample space represented by capital S. So now I am saying I have three events. One is A, one is B, another one is C. So I can divide this here. So suppose this is some event A, this is some event B, and this is some event C. So in this case, A is this one, B is this one, and C is this one. So that means they are not intersecting each other. So when you add up all these, they will completely make up the sample space. So when you take the union of A union B union C, that would be equivalent to the whole sample space. Whereas if you take the intersection of A with B, or of B with C, or of C with A, that intersection is empty. That means they have nothing in common, but when you add them, when you get the total of these, so that will make up the whole of the sample space. So that is mutually exclusive events. And then the next is independent events. So what are independent events? Independent events are those whose occurrence does not affect the occurrence of others. For example, suppose you are tossing a coin and at the same time you are sowing the seeds, and at the same time you are listening to music. So that means these are three events. Let us call this as event A, the sowing of seeds as event B, and listening to music at event C. So now these three events, they do not affect each other. That means if you toss a coin, that has nothing to do with your sowing seeds or your listening to music, but whereas the other two, they are also independent of each other. That means the occurrence of one does not affect the occurrence of others. And in this case, we have this result that we will study later, that the probability of the intersection of A and B, that is equal to probability of A multiplied by the probability of B. So this result we will study more in the later part. So this is independent events. The next is equally likely events. Equally likely events are those which can occur in without preference to each other. That means the occurrence of one does not is equally likely. So what does it mean? It means that there is no preference which is given to one kind of event, and they have equal chances of occurring. They have equal chances of occurrence.
Ma'am, your voice is lagging.
Okay. So equally likely events are those which have equal chances of occurrence, and they are not given any kind of preference to each other. For example, when you toss a coin, so the occurrence of head and the occurrence of tail, they are equally likely, because 50% of the time head will come up and 50% of the time tail will come up. So no preference is being given to either of head or tail. So that is the meaning of equally likely events. So now getting to know about all these things, random experiment outcomes, what are events trials, exhaustive cases, favorable cases, mutually exclusive cases, independent events, equally likely events. Let us now move on to the more formal definition of probability, which says that in a random experiment in which there are n exhaustive, mutually exclusive and equally likely outcomes, out of which m are favorable outcomes of the event A, then the probability of an event A is defined by the number of favorable outcomes divided by the total number of outcomes. So that means we are performing some kind of random experiment, and from that random experiment we have n as the exhaustive, that means total number of outcomes are n which are mutually exclusive, that means one is not depending on other, that means their intersection is empty, they have nothing in common, and the outcomes are equally likely outcomes, that means no outcome is given preference over others. And so out of these total outcomes, we are saying we have m as the favorable number of outcomes. So the probability of occurrence of event A would be equal to the favorable number of outcomes divided by the total number of outcomes. For example, we have two dice that are tossed. So we are asked what is the probability of getting the sum 6 and the sum 9. So first of all, we should know what are the exhaustive outcomes of this particular experiment. The experiment is we have tossed two dice. So in one dice, when you throw one die, the possible outcomes are 1, 2, 3, 4, 5 or 6. Out of these 6 numbers, you will get one number. If you throw another die, on that die you will again get out of these 6 numbers one number. So when you throw the two dice together, so that means one number will appear on first die and second number will appear on second die. So let us make the exhaustive cases for this. So we'll place them in the sample space. So either you would have 1 on each of these, or 1 on first, 2 on second, or 1 on first, 3 on second, or 1 on first, 4 on second, 1 on first, 5 on second, 1 on first, 6 on second, and so on. So you would then have 2 on first, and then 1, 2, 3, 4, 5, 6 on the second, then 3 on first, 1, 2, 3, 4, 5, 6 on the second, 4 on first, 1, 2, 3, 4, 5, 6 on the second, 5 on first, 1, 2, 3, 4, 5, 6, and 6 on first, 1, 2, 3, 4, 5, 6. So in total, we have how many exhaustive cases? The total number are 36. 6 for first die and 6 for second die. So we have 6 to the power 2 here. 6 multiplied by 6, that is 36. So these are the total number of cases. So now, in order to calculate the probability, we should know first what is the favorable number of cases, for which we have the sum equal to 3. So that means the sum on both the die should be equal to 6. So let us identify those. When you add the numbers, in this case 1, 5, you have the sum as 6, and then you have the sum as 6 in the case 2, 4, and then you would have for 3, 3, and then you would have it for 4, 2, and then 5, 1. So in total, you would have 1, 2, 3, 4, 5 cases which are showing the sum as 5. So here the favorable cases are, these are 1, 5, 2, 4, 3, 3, and then 4, 2, and then 5, 1. So in total we have 5 cases and total are 36. So that means the probability would be number of favorable cases divided by the total number of cases. So that would be 5 divided by 36. So this is the probability of having sum as equal to 5. And next we will see what is the probability of getting a sum equal to 9. So here the sum equal to 9 is obtained for the case 3, 6, 4, 5, 5, 4, and 6, 3. For only these digits, when you add these digits, 3 plus 6 that is 9, 4 plus 5 that is 9, 5 plus 4 that is 9, 6, 3 that is 9, 6 plus 3 that is 9. So that means there are only 4 cases that are available. So favorable cases total are 4, which are 3, 6, 4, 5, 5, 4, and 6, 3. So these are 4 favorable cases out of 36 total cases. So the probability here would be 4 divided by 36, that is equal to 1 divided by 9. So this is the probability in this case. So let us see one more example, one more question. The question says you have to calculate the probability of getting 53 Sundays whenever there is a leap year is selected at random. So out of all the years, one year is selected at random, that is the leap year. What is leap year? It has 366 days. In total it has 366 days, and one, that means you got 29 days in the month of February, right? So this is the condition for leap year. Now how many weeks are present in 366 days? So you will divide this 366 by 6, so you will have 52 weeks and 2 days are remaining and 2 days more. So that is the number of weeks that are present in this 366 days. So now we are to check what is the probability of getting a Sunday. So how can, out of this 52 weeks, 53 weeks would be available when out of these 2 days, 1 day is Sunday. So first of all, let us see all the exhaustive cases. All the exhaustive cases. So out of this pair of 2, either it could be Sunday, Monday, or it could be Monday, Tuesday, or it could be Tuesday, Wednesday, or it could be Wednesday, Thursday, right? And it could be Thursday, Friday, or it could be Friday, Saturday, or it could be Saturday, Sunday. So these are the only possibilities that you have. So in total this forms the sample space. So that means how many possibilities are present? One is Sunday, Monday, that is 1. Then another is Monday, Tuesday, that is 2. Another is Tuesday, Wednesday, that is 3. Another is Wednesday, Thursday, that is 4. Then Thursday, Friday, that is 5. And then Friday, Saturday, that is 6. And then Saturday, Sunday, that is 7. So in total we have total exhaustive cases, or the total number of outcomes, as 7. Now the favorable outcome is the one in which we are having Sunday. So the favorable outcome here is the first one, that is Sunday, Monday, and the last one, that is Saturday, Sunday. So that means the favorable number of cases here would be, favorable number of cases would be 2. So the probability of getting 53, the probability of getting 53 Sundays in a leap year would be 2 divided by 7. Number of favorable cases, that is 2, divided by the total outcomes, that is 7. So this is the probability, 2 divided by 7. Next we have random variable. So this is the definition, which states that we have to tell what is a random variable. Random variable is a function. What a function do? A function takes some elements from some domain and map them to a unique element present in the domain range, right? So random variable is a function which maps the elements from the set of outcomes. Set of outcomes is basically what? It is the sample space. So it is the sample space. So it takes the elements from sample space and map them to some real number. That means it gives a digit to it. It provides a number to it. For example, let me show you this example. The example is, we are assuming that there are 2 coins which are tossed simultaneously. So we have 2 coins and we are tossing them together, and the number of heads are to be noted. So that means the favorable cases here is, favorable cases here are, we have to check what is the number of heads. So they are saying we have to construct a random variable for this situation. So that means we have to first see what are the outcomes, total outcomes, or we have to first draw the sample space. So how could you draw the sample space? The sample space is drawn when you list all the outcomes. So first of all, you see what is your experiment. The experiment you have is you are tossing 2 coins. With one coin, the outcomes would be head or tail. With another coin, the outcome would be either head or tail. So you could have as a combination either head or as head on one, tail on another, or tail on first, head on second, or tail on first, tail on second. So these are the only possible cases that you can have. So out of these possible cases, we have to see what are the number of heads that we are getting. So we have to draw a random variable for this. So I am naming the random variable to be capital X. So capital X denote the random variable, which means I am drawing a table in which I have listed all the outcomes of the given experiment. They are head, then head tail, then tail head, and then tail. So these are the 4 possible outcomes. Now I have to define a function whose answer is a digit. So that means I am defining x from sample space to the set of real numbers. That means, and what should x denote? It should denote the number of head. So in the first outcome, if you have head, so x would represent 2 because x here represents the number of heads which are present in that particular outcome. So in the first case, head, the number of outcomes present is 2. In the second case, head, tail, the number of outcomes present is 1. In the third case, tail, head, the number of heads which are present is 1. And in the last case, tail, the number of heads which are present is 0. So that means this x representing 2, 1, 1, 0, that forms the random variable for the given experiment. So now with all these definitions, we are ready to see another definition of probability, which says that if we are given a sample space S, then for each event A of S, whatever is the sample space, for every event A of S, which is obviously a subset of S, that means we are picking that event up from the sample space only, there is associated a number P of A. And what is this P of A? This is known as the probability of the event A, such that the axioms of probability are satisfied. So what is the first axiom? It says that the probability of any event, whatever event you take from the sample space, it will always lie between 0 and 1. This is the first axiom. The second axiom says that whole of the sample space has probability equal to 1. What does it mean? It means you are taking the favorable cases as the total number of cases. So favorable cases is equal to total number of cases. So by a definition of probability, favorable cases divided by total number of cases would be equal to 1 because they will cancel out each other. So probability of sample space would be equal to 1. And the last axiom is that for mutually exclusive events A and B, mutually exclusive events means they have nothing in common. So that means the intersection of event A with event B is equal to 5. That means they are non-empty. So in that case, the probability of A union with B, that is equal to the probability of A plus probability of E. Otherwise we have this formula that probability of A union B that is equal to probability of A plus probability of B, P of B, minus probability of A intersection B, P of A intersection B. So this is the formula. But for mutually exclusive cases, as there is the intersection of A and B is empty, that is phi, that means the probability of A intersection B is equal to 0 because there is nothing present in that phi. That is why the probability is 0. And we have this result, probability of A union B is equal to probability of A and probability of B. So if you have any doubts, you can ask.